The universe hides structures that should not exist. We are about to embark on a journey to the very frontiers of known science, exploring 25 cosmic formations that defy our current understanding of physics. From galaxies made of almost nothing to voids of impossible emptiness, each one is a profound mystery waiting to be solved. By the end, you will have a new perspective on just how strange and uncharted the cosmos truly is. We will encounter a perfect ring galaxy with no explanation and a gravitational pull from beyond our visible universe. What cosmic discovery do you think will challenge everything we know? Our journey begins in a place of profound silence. Nestled within the constellation of Boötes, the herdsman, lies a spherical region of space so vast and so empty it has earned a chilling nickname, the Great Nothing. This is the Boötes Void. To grasp its scale, picture our own Milky Way galaxy. Now imagine a sphere around it so enormous that it would take a beam of light 330 million years to travel from one side to the other. Within that incomprehensible volume, astronomers expected to find thousands, even tens of thousands of galaxies. Instead, they have catalogued only a few dozen. It is a cosmic desert of staggering proportions, a bubble of near nothingness in a universe we thought was uniformly sprinkled with islands of stars. Its discovery was a direct challenge to one of astronomy's foundational ideas, the cosmological principle. This principle states that on the largest scales, the universe should look roughly the same in every direction, with matter distributed fairly evenly. The Boötes Void is not even. It is a glaring exception, a hole in the cosmic fabric that seems to defy the rules. How could such a thing form? One leading theory suggests it is not a single void, but the result of several smaller voids merging together over eons, like soap bubbles combining into one gigantic cavity. Another, more unsettling idea is that we are simply witnessing a statistical fluke, a one-in-a-million chance occurrence that, by pure luck, exists right in our observational backyard. But the sheer scale of the emptiness makes that possibility feel almost as strange as the void itself. It forces us to question whether our models of the universe's structure are complete, or if we are missing a fundamental piece of the puzzle that allows for such immense and haunting pockets of nothing. From a realm of shocking emptiness, we now confront its opposite, a structure of such immense density and scale it seems to rewrite the rules of cosmic architecture. This is the Hercules corona Borealis Great Wall, the single largest known object in the entire observable universe. Its dimensions are almost impossible to comprehend, a gargantuan filament of superclusters stretching over 10 billion light-years from end to end. To put that into perspective, if you could travel at the speed of light, it would take you longer to cross this one structure than the current age of our planet Earth. It was not discovered by looking at galaxies directly, but by mapping the brightest, most violent explosions in the cosmos, gamma-ray bursts. These fleeting flashes of energy act like cosmic lighthouses, and when astronomers plotted their locations, a staggering pattern emerged, revealing this titanic wall of galaxies hidden in plain sight. Its existence presents a direct and profound challenge to a key cosmological idea known as the end of greatness. This principle suggests that beyond a certain scale, the universe should become smooth and featureless, like looking at a vast ocean from high above where individual waves blend into a uniform surface. The Hercules corona Borealis Great Wall is a wave so colossal it should not exist according to that model. It is a continent in the cosmic ocean, a structure so large it implies the universe might not be truly homogeneous or evenly mixed on the very largest scales we can observe. This forces a difficult question: are we seeing a statistical anomaly of unimaginable rarity, or is our fundamental understanding of the universe's structure missing a critical chapter? The wall stands as a silent, monumental rebuke to our assumptions, proving that the cosmos still holds formations capable of dwarfing not just our imagination, but our very theories of reality. Yet the cosmos seems determined to test the very idea of limits, for there is another contender for the title of largest structure, one that was discovered even closer to home. This is the Sloan Great Wall, a colossal filament of galaxies mapped in stunning detail by the Sloan Digital Sky Survey. If the Hercules Corona Borealis Great Wall is a continent, then the Sloan Great Wall is a sprawling mountain range, still unimaginably vast at over 1.3 billion light-years in length, but residing a bit closer in our cosmic neighborhood. Its discovery painted a new picture of the universe's large-scale structure, revealing an intricate web of superclusters and voids that looks almost like the neurons of a gigantic brain. The existence of two such titanic walls, however, raises a fascinating and heated debate among cosmologists. Are these two separate, independent structures, or could they be connected parts of an even larger, unfathomable pattern we cannot yet see? Some analyses suggest they might be linked by a faint bridge of galaxies, implying we are looking at different segments of a single, universe-spanning filament. This debate is not just academic, it cuts to the heart of how the universe organized itself after the Big Bang. These walls are not random accidents, they are the fossilized imprints of the earliest seeds of structure, magnified by gravity over billions of years. Their scale and density point directly to the invisible architect of the cosmos, dark matter. It was the gravitational pull of dark matter that first drew ordinary matter into these vast sheets and filaments, providing the scaffolding upon which all visible galaxies were built. So when we look at the Sloan Great Wall, we are not just seeing a collection of stars, we are seeing the ghostly outline of dark matter's dominant hand, a cosmic blueprint from a time when the universe was in its infancy. The fact that we can find two such immense blueprints forces us to ask just how common are these structures, and what does their sheer size tell us about the mysterious dark force that shaped them? While those immense walls trace the universe's largest scales, our next mystery focuses on a single, impossibly perfect island of stars. In the faint constellation of Serpens, a cosmic jewel hangs in the void known as Hoag's object. Through the lens of the Hubble Space Telescope, it appears almost artificial, a stunningly precise ring of brilliant blue stars encircling a dense, golden core of older stars, with a dark, seemingly empty gap separating the two. It looks less like a galaxy and more like a celestial donut or a giant's thrown smoke ring frozen in space. This perfection is its greatest puzzle. Typically, ring galaxies like the famous cartwheel are formed by violent, head-on collisions where a smaller galaxy punches through the center of a larger disk galaxy. The gravitational shockwave triggers a wave of star formation that ripples outward, creating a temporary ring. But Hoag's object shows no signs of such a traumatic recent event. There is no visible culprit galaxy nearby, and its core sits perfectly centered within the ring, undisturbed. If a collision created this, it happened so long ago that all evidence should have faded, yet the ring remains spectacularly sharp and symmetrical. This leads astronomers to a fork in the road of cosmic explanation. One possibility is that we are witnessing the extremely rare aftermath of a galactic merger that occurred billions of years in the past, a fossilized ring that has somehow maintained its perfect form against all odds. The other, more radical idea is that Hoag's object represents an entirely different evolutionary path for galaxies, one where internal instabilities or gravitational resonances slowly sculpted a disk into this perfect form without any outside intervention. It stands as a serene and beautiful challenge, a reminder that for every rule we deduce about how galaxies live and evolve, the universe may have crafted a breathtaking exception. The serene perfection of Hoag's object gives way to a discovery of such staggering scale it seems to bend the very rules of the cosmos. Announced in just 2021, the giant arc is a colossal, crescent-shaped structure spanning an almost unbelievable 3.3 billion light-years across the sky. It was not found by looking at galaxies, but by staring into the brilliant hearts of distant quasars, the active supermassive black holes that are the universe's most powerful lighthouses. As the intense light from these quasars travels billions of years to reach us, it passes through vast clouds of intergalactic gas. Within that gas are atoms of magnesium stripped of one electron. These ions absorb specific colors from the quasar's light, leaving a unique fingerprint in the spectrum. By mapping where these magnesium fingerprints appeared across dozens of quasars, astronomers noticed a pattern, a graceful, nearly symmetrical arc of absorption that traced the outline of something immense. Think of it like using a flashlight to see the outline of your hand in a foggy room. You are not seeing the hand itself, but the shadow it casts in the mist. That shadow, in this case, is the giant arc, a filament of galaxies and gas so vast it covers roughly 1/15 of the observable universe. Its size is the problem. Just like the Great Walls we discussed, the giant arc's dimensions directly confront the cosmological principle, the idea that matter should be evenly distributed on the largest scales. Finding a structure this big is like stirring a cup of coffee and finding, once everything settles, that all the grounds have arranged themselves into a single, perfect ring clinging to the side. It defies our expectation of randomness. The implications are profound. If the giant arc is confirmed by further observations, it means our standard models of cosmic evolution, which predict a limit to how large structures can grow, are either incomplete or fundamentally wrong. It hints at unknown forces or initial conditions from the Big Bang that imprinted these mega structures onto the fabric of space-time itself. This arc is not just a collection of galaxies, it is a question mark written across the sky in magnesium and light, asking us how well we truly understand the architecture of everything. Perhaps the most unsettling aspect of these cosmic megastructures is that we may be living inside one. Our home, the Milky Way galaxy and its local group of neighbors, does not float in an average part of the cosmos. Instead, we reside within the KBC Void, a colossal spherical bubble named for the astronomers Keenan, Barger, and Cowie who identified it. This void is immense, roughly 2 billion light-years across, and it is characterized by a significantly lower density of matter compared to the universal average. We are not in a desert as extreme as the Boötes Void, but we are certainly in a spacious suburb, a relative underdensity on a staggering scale. This fact transforms the KBC Void from a simple curiosity into a profound complication for modern cosmology. Our entire understanding of the universe's expansion, its age, and its fate is built upon measurements we take from this one specific location. And if our neighborhood is emptier than most, it could be subtly distorting everything we see. This leads us directly to one of the most pressing mysteries in science today, the Hubble tension. In simple terms, we have two primary ways to measure how fast the universe is expanding. One method looks at the ancient light from the early universe, the cosmic microwave background, and extrapolates the expansion rate from there. The other method uses relatively nearby stars and supernova as mile markers to measure the expansion rate directly in our cosmic present. These two methods, both meticulously checked and rechecked, yield different answers. They disagree by a small but significant amount, a discrepancy that has stubbornly resisted all explanations. Now consider our position inside the KBC Void. Living in a local underdensity is like standing in a valley while trying to measure the slope of an entire mountain range. The gravitational pull of the denser regions outside our bubble is subtly different. Matter, including our galaxy, might be flowing slightly toward those denser areas, and this local motion could be skewing our measurements of the universe's overall expansion from this specific vantage point. The void we call home might be acting as a cosmic lens, warping our perspective just enough to create this frustrating and pivotal disagreement. Solving the Hubble tension could very well require us to first fully map and understand the peculiar emptiness of our own celestial backyard, a reminder that sometimes the greatest mysteries begin right where we are. This disagreement over our cosmic address points toward an even stranger motion, one that seems to defy the very geometry of space itself. Astronomers have detected a mysterious and relentless current sweeping through the cosmos known as the dark flow. It is not the expansion of the universe, but something far more peculiar. Hundreds of distant galaxy clusters, each containing thousands of galaxies, appear to be streaming in the same specific direction at astonishing speeds of over 2 million miles per hour. This coordinated motion was discovered by studying the oldest light we can see, the cosmic microwave background. As these massive clusters move, their hot gas interacts with this ancient radiation, creating a subtle but detectable temperature shift, a kind of cosmic wake. By mapping these shifts, scientists could trace the direction and speed of the cluster's motion. The result was shocking. These clusters, spread across billions of light years, are not moving randomly. They are all being pulled, like leaves caught in a river, toward a single point in the sky beyond the constellation Centaurus. The most unsettling part is that the source of this pull appears to lie far beyond the edge of our observable universe. Within the cosmos we can see, there is no known structure massive enough, no collection of galaxies or dark matter that could generate such a powerful and coherent gravitational tug. This presents a direct challenge to a core principle called isotropy, the idea that the universe should look and behave the same in all directions. The dark flow suggests it does not, that there is a preferred direction imprinted on the cosmos by something we cannot see. Naturally, a discovery this radical sparked intense debate. Skeptics argue it could be a statistical fluke, an artifact of how the data was processed, or perhaps the gravitational influence of a nearby but still unseen superstructure, a sibling to the Great Walls we have already discussed. Yet the signal has persisted through multiple analyses. This leads other scientists to contemplate possibilities that sound like science fiction. Could the dark flow be the gravitational pull of a massive structure in a neighboring universe, a parallel cosmos brushing against our own in the greater multiverse? Or does it point to a pre-Big Bang imprint, a scar from the birth of our universe that set everything in motion? The dark flow remains one of cosmology's most profound and contentious puzzles, a silent river in the dark, hinting that our universe is not an island, but perhaps just one piece of a reality far grander and more connected than we ever dared to dream. But the flow of galaxies is not the only anomaly written in the ancient light. There is a place in the infant universe that simply does not make sense. In the all-sky map of the cosmic microwave background, the faint afterglow of the Big Bang, there is a feature known simply as the cold spot. It is a vast circular region, significantly colder than the average temperature of its surroundings, a cosmic chill that has persisted through observations by both the WMAP and the Planck satellites. This is not a minor fluctuation. While the background radiation is famously smooth, dotted with tiny, expected temperature variations, the cold spot is an outlier, a statistical anomaly so large that some researchers argue it should not exist at all. It is a fossil, an imprint from when the universe was less than 400,000 years old, and its coldness presents a riddle with profound implications. One leading explanation is as elegant as it is strange. It could be the signature of a cosmic texture. In the frenetic moments following the Big Bang, as the fundamental forces of nature separated from one unified force, the fabric of space-time itself may have undergone a phase transition, like water freezing into ice. And just as ice can form cracks and defects, this cosmic freezing might have left behind tangled knots in space-time, regions where the very vacuum of space has a different energy. If such a texture existed and later decayed, it would have left a distinct cold imprint on the cosmic microwave background, exactly like the one we see. The cold spot, then, could be a scar from the universe's violent birth, a one-in-a-million relic we were lucky enough to find. Another theory ventures into even more speculative territory. Could the cold spot be a bruise, evidence of a colossal collision with another universe in the vast multiverse? In this mind-bending scenario, our observable cosmos might have bumped into a neighboring bubble universe in its earliest moments. The energy of that collision could have drained away from a region of our sky, leaving it colder, a permanent mark of contact with a reality beyond our own. Of course, there is a more conventional possibility. Perhaps the cold spot is not a primordial feature at all, but a later illusion created by a giant supervoid, an enormous, mostly empty region of space lying between us and the ancient light. As light from the cosmic microwave background passes through such a void, it loses a tiny amount of energy climbing out of the void's gravitational well, a process called the integrated Sachs-Wolfe effect. This would make the light appear cooler to us. The problem is measurement. Astronomers have searched for a void large enough to cause the observed cooling, and while they have found an underdensity in that direction, it does not seem nearly vast or empty enough to account for the extreme temperature drop of the cold spot. The void explanation, while plausible, feels insufficient, leaving the more exotic theories on the table. So we are left with a choice between cosmic archaeology and cosmic collision, between a defect in space-time and a brush with another reality. The cold spot remains a quiet, persistent chill in the data, a whisper from the dawn of time that we have yet to fully understand. The chill of the cold spot feels impossibly distant, a relic from the universe's first moments. Yet some of the most stubborn cosmic mysteries are not found in the far reaches of deep space, but right here in our own celestial neighborhood, orbiting our very own galaxy. Look at the Milky Way and you see a majestic spiral. Around it, astronomers have discovered dozens of smaller dwarf galaxies, each containing perhaps only a few billion stars. According to our leading model of cosmic evolution, the Lambda CDM model, these satellites should be scattered around us in a roughly spherical, random swarm like bees buzzing around a hive. But they are not. A significant number of them, including the famous large and small Magellanic Clouds, are not buzzing randomly at all. Instead, they are moving with startling coordination, orbiting the Milky Way within an incredibly thin, rotating plane. Picture the planets in our solar system all orbiting the Sun in a single, flat disk. That is precisely what we see with these satellite galaxies, a vast cosmic carousel over 1 million light-years wide. They are not just in the same general area, they are aligned with mathematical precision, moving together like dancers in a grand gravitational ballet. This discovery, known as the satellite plane or disk of satellites, is a profound headache for cosmologists. The Lambda CDM model, which has been spectacularly successful at explaining the universe on the largest scales, predicts that dark matter halos, the invisible cocoons that host galaxies, should accumulate smaller satellite halos from all directions. These satellites should then fall into orbit from random angles, creating a messy, three-dimensional cloud. The existence of a thin, rotating plane is like throwing a handful of marbles into the air and watching them all arrange themselves into a perfect spinning disk before they land. It defies the odds completely. So how did this happen? One compelling theory points to a violent event in our galaxy's past. Billions of years ago, the Milky Way may have collided with a large satellite galaxy, an event that would have sent powerful ripples or density waves through its dark matter halo. These waves could have corralled many of the smaller dwarf galaxies, herding them into the same orbital plane we see today. It is a cosmic roundup with the gravitational shockwave from a long-ago crash acting as the shepherd. Another, more radical idea challenges the very nature of these satellites. Perhaps they are not ancient, primordial galaxies that fell into the Milky Way's grasp independently. Instead, they could have been born more recently from a single, colossal event, like a titanic collision between the young Milky Way and another large galaxy. The debris from such a crash, rich in gas and stars, could have coalesced into multiple dwarf galaxies that all inherited the same motion, like fragments from a single exploding shell all traveling in the same direction. This would make them a family, not a random collection of strangers explaining their coordinated dance. Three-dimensional simulations of this orbital plane reveal its stunning geometry, a vast, tilted disk slicing through the halo of our galaxy. Its continued existence is another puzzle, as gravitational tugs from the Milky Way and from the satellites themselves should have disrupted such a delicate arrangement over billions of years. The fact that it persists means either the plane is younger than we think, or some unseen force is helping to maintain its precise structure. This mystery brings the challenge of cosmic architecture right to our doorstep, proving that even our own home galaxy holds formations that our best models struggle to explain. This galactic mystery leads us to a more recent and violent discovery, one that rises from the very heart of our own Milky Way. In 2010, scientists analyzing data from the Fermi Gamma Ray Space Telescope uncovered a pair of colossal structures, each a titanic bubble of high-energy gamma rays. These are the Fermi bubbles, and they form a near-perfect hourglass shape, ballooning out from the galactic center for 25,000 light-years both north and south of the galactic plane. To visualize their scale, if our eyes could see gamma rays, this structure would dominate 1/3 of the visible sky, a vast, ghostly hourglass standing sentinel over the galaxy. For something so enormous to have remained hidden until the 21st century is astonishing, a testament to how much of the universe's most energetic activity is invisible to our traditional telescopes. The bubbles are not solid objects, but vast lobes of superheated gas, each one a cosmic pressure cooker where particles are accelerated to near light speed, colliding to produce the brilliant gamma-ray glow that finally gave them away. Their discovery immediately posed a fundamental question: what titanic event could have blown these bubbles into the fragile halo of our galaxy? The prime suspect sits at the very location from which the bubbles emanate, our galaxy's own supermassive black hole, Sagittarius, a star. While it is relatively quiet today, the Fermi bubbles suggest it was anything but tranquil in the past. One leading theory is that several million years ago, Sagittarius, a star, experienced a cataclysmic feeding frenzy, devouring an enormous cloud of gas or even a star. The incredible influx of material would have triggered a violent outburst, a pair of relativistic jets erupting from the black hole's poles. These jets, focused beams of energy and matter traveling at nearly the speed of light, would have punched through the surrounding gas, inflating these gigantic cavities like a cosmic blowtorch. The bubbles we see today would be the fossilized remnants of that ancient eruption, a scar from a time when the heart of the Milky Way roared. However, there is another compelling suspect. The galactic center is also home to a dense, bustling region of star formation. If, in the past, there was a period where hundreds of massive stars were born and then died in rapid succession as supernova, the combined force of all those stellar explosions could have created a powerful galactic wind. This wind, a tsunami of energy, could have blown outward in two opposite directions, sculpting the bubbles we observe. This stellar explanation points to a more distributed, chaotic violence rather than a single, focused eruption from the black hole. The ongoing debate between these two origins is crucial because it challenges our understanding of galactic ecology. We once thought of galaxies as relatively stable islands with quiet centers and halos of diffused gas. The Fermi bubbles prove that the galactic center is an engine capable of violent outbursts that can reshape its entire surroundings, heating the galactic halo and potentially regulating star formation across vast distances. They are a stark reminder that our Milky Way has a dramatic and explosive history written in gamma rays across the sky, a history we are only just beginning to read. The explosive history of our galaxy is written not just in gamma rays, but in a delicate, ghostly ribbon of gas that stretches across nearly half the southern sky. This is the Magellanic Stream, a river of hydrogen over 600,000 light-years long, torn from our two largest satellite galaxies, the Large and Small Magellanic Clouds, as they dance around the Milky Way. For decades, it was seen as a classic example of a tidal tail, a simple trail of debris left behind by gravitational forces, much like the wake behind a boat. But the closer astronomers looked, the more puzzling the stream became. Its sheer mass is staggering, containing over 1 billion times the mass of our Sun in gas, and it has remained in a remarkably coherent, narrow band despite the immense gravitational tides of our galaxy. Simple tidal models struggle to explain how something so massive could stay so neatly bundled together over billions of years without dissipating into a shapeless cloud. The stream was holding a secret, and the clue lay in what was holding the stream together. The leading theory to solve this mystery involves an invisible actor, a massive halo of dark matter. Astronomers now suspect that the Magellanic Clouds are not just two lonely galaxies, but the brightest members of a larger, unseen entourage. They are thought to be shrouded in an extensive common envelope of dark matter, a vast, invisible cocoon that they travel within. When the clouds had a closer encounter with each other in the distant past, and as they feel the relentless pull of the Milky Way, it was this dark matter halo that provided the crucial gravitational scaffolding. It acted like a cosmic net, helping to wrench the gas out of the galaxies while also keeping the resulting stream confined and organized, preventing it from flying completely apart. This transforms the Magellanic Stream from a simple debris field into a unique and powerful laboratory. By studying the dynamics and structure of this luminous ribbon of gas, scientists can indirectly map the properties and distribution of the dark matter that surrounds its parent galaxies. It offers a rare chance to measure how much dark matter dwarfs possess and how it behaves during galactic interactions, a process that is fundamental to the growth of all large galaxies. Wide-field images that trace the stream's faint, shimmering arc across the void are not just pictures of lost gas. They are a shadow puppet show, revealing the silhouette of the invisible dark matter hand that sculpted it. Our own galaxy is caught in a vast, silent river. The Milky Way, along with our entire local group of galaxies and thousands of others, is being pulled toward a specific point in intergalactic space, a mysterious region of immense gravity known as the Great Attractor. For decades, this was one of astronomy's most frustrating puzzles, not because we could not feel its pull, but because we could not see it. Its location lies directly behind the dense plane of our own galaxy, in an area astronomers call the zone of avoidance. Here, thick clouds of cosmic dust and billions of stars in the Milky Way's disk block our optical view, creating a blinding fog that hid the source of this colossal tug. It was like trying to find a lighthouse while standing in the middle of a blinding sandstorm. We knew the current was there, we could measure our motion through space, but the origin of the flow remained shrouded in darkness. The breakthrough came not by piercing the dust with visible light, but by using instruments that could see through it. Radio, infrared, and X-ray telescopes began to map the hidden landscape. What they revealed transformed our understanding. The Great Attractor is not a single, unimaginably dense object, but the gravitational center of our home supercluster, an immense web of galaxies now named Laniakea, which means immense heaven in Hawaiian. Think of it not as a drain, but as the deepest valley in a vast, rolling gravitational landscape. All the galaxies in our local region are sliding down the slopes of this cosmic basin toward its point of lowest gravitational potential. We can visualize this with stunning flow maps, where the motions of thousands of galaxies are traced like streams of water, all converging toward this one central region. Yet, even with this grand realization, a mystery lingers. The sheer strength of the pull, the speed at which we are being drawn in, suggests there is more mass concentrated there than we can account for by counting the visible galaxies. Once again, the ghostly hand of dark matter seems to be at work, providing the extra gravitational anchor needed to explain the motion. The Great Attractor, therefore, stands as a monumental lesson. It is both a solved puzzle and an ongoing revelation, exemplifying our quest to map the hidden architecture of the cosmos. We have found the valley, but we are still counting the unseen stones that form its slopes, reminding us that the true shape of our universe is often written in gravity, not just in light. The gravitational valleys of Laniakea shape the motions of galaxies, but within the vast flows of gas and dust, the cosmos sometimes sculpts forms of startling, almost mathematical precision. Among the billowing clouds of stellar nurseries and the chaotic remnants of stellar death, one structure stands apart for its unnatural geometry. This is the Red Rectangle Nebula, a cosmic masterpiece surrounding the aging star HD 44179. When the Hubble Space Telescope first turned its gaze upon it, astronomers were met with a sight that defied all expectations. Instead of the soft, ethereal glow of a typical planetary nebula, they saw a stark architectural wonder. Two brilliant beams of light, like searchlights, shoot in opposite directions from a central star, and connecting them is a series of perfectly concentric, rectangular rungs of glowing gas and dust. It looks less like a celestial object and more like a ladder or a giant, glowing honeycomb suspended in the void. This bizarre, box-like structure is utterly unique in the known universe, and its sharp, symmetric edges present a profound puzzle. How can the violent, chaotic processes of a dying star produce something so geometrically perfect? The leading explanation involves a delicate and rare cosmic ballet. At the heart of the nebula, the central star is in its final stages, shedding its outer layers into space. Crucially, astronomers believe this star is not alone. It likely has a close companion, a smaller star locked in a tight orbit. This binary dance is the key. As the primary star expels its material, the gravitational influence of the companion star funnels that outflow into a dense, thick disk of dust and gas that encircles them both like a giant cosmic donut. Then, from the poles of the system, perpendicular to this disk, powerful jets of energy and matter erupt. These jets, constrained and shaped by the dense central disk, punch through the surrounding material, creating the two bright beams. The stunning rectangular rungs are thought to be the result of periodic outbursts from the star. Imagine waves of material being ejected in pulses, like rings of smoke from a pipe. But because they are squeezed outward by the thick disk, they expand not as spheres but as conical shapes. From our vantage point, looking nearly edge-on at this disk, those conical shells of gas appear to us as a sequence of perfect rectangles, a cosmic illusion of perspective and physics. Beyond its breathtaking beauty, the red rectangle serves as a vital scientific laboratory. Its dense dust clouds are a chemical factory, and within them, astronomers have detected some of the most complex organic molecules ever found in space. These include polycyclic aromatic hydrocarbons, large, stable molecules built from rings of carbon and hydrogen. These are not life itself, but they are considered fundamental building blocks, the raw materials from which more complex prebiotic chemistry could arise. The nebula is, in essence, forging the very seeds of potential future life and scattering them into the interstellar medium. The high-resolution Hubble imagery reveals this process in exquisite detail, showing the intricate latticework of dust lanes and the vibrant red glow of hydrogen gas excited by the central star's intense ultraviolet light. The Red Rectangle Nebula stands as a testament to the universe's capacity for both chaos and order, a place where a dying star's final act creates not just a fleeting cloud, but a structured, geometric monument, all while quietly assembling the complex carbon chemistry that is the foundation of life itself. But geometric perfection is not confined to the distant deaths of stars. One of the most startling and persistent patterns in our entire solar system spins at the top of a gas giant, a shape so precise it looks drawn by a cosmic compass. This is the hexagon on Saturn, a vast, six-sided jet stream cloud pattern crowning the planet's north pole. Captured in breathtaking detail by the Cassini spacecraft, this structure is a true giant, with each side longer than the diameter of Earth. It is not a solid object, but a swirling, turbulent river of clouds moving at hundreds of miles per hour. yet it maintains its razor-sharp, hexagonal geometry for decades, perhaps even centuries. How can such a rigid, angular form emerge and hold its shape in the chaotic, fluid atmosphere of a planet? This question defies our conventional understanding of meteorology and fluid dynamics. On Earth, weather patterns are dominated by swirling circular vortices and meandering waves, not locked into permanent polygons. The hexagon's very existence suggests that the rules governing planetary atmospheres can produce phenomena far stranger than anything we experience here. Scientists believe the key lies in the deep, hidden layers of Saturn's atmosphere and the planet's rapid rotation. Laboratory experiments and sophisticated computer simulations offer a compelling clue. When a circular tank of fluid is rotated at different speeds with a smaller, faster rotating cylinder at its center, the fluid between them can spontaneously organize into stable polygonal shapes. This suggests that the hexagon might be a standing wave pattern, a kind of persistent ripple in Saturn's fast-moving jet stream, created by differences in wind speed at different latitudes. The hexagon's stability likely comes from its great depth, possibly extending hundreds of miles down into the atmospheric abyss, where it is anchored by forces we cannot directly see. The stunning Cassini footage reveals more than just the hexagon's outline. Within its boundaries, smaller vortices swirl and dance, and the entire structure changes color with Saturn's seasons, shifting from a deep blue to a golden haze over time. This atmospheric anomaly serves as a powerful reminder that profound cosmic mysteries are not always billions of light years away. They can exist right in our own celestial backyard, on a world whose cloud tops hide processes we are only beginning to fathom. The hexagon stands as a monumental lesson in humility, a six-sided question mark etched into the clouds of another world, challenging us to rethink what is possible in the dynamic skies of planets. The stark geometry of Saturn's hexagon is a mystery of physics, but it pales before a signal from the void that carried the eerie signature of intelligence. On a quiet Ohio night in August 1977, the Big Ear radio telescope, methodically scanning the sky as part of the search for extraterrestrial intelligence, recorded something extraordinary. A narrowband radio burst 72 seconds long rose from the background noise in the constellation Sagittarius. It was so powerful and so perfectly tuned that when volunteer Jerry Amon saw the computer printout, he simply circled the alphanumeric sequence and wrote a single, emphatic word in the margin: "Wow." That iconic printout, with its circled 6EQUJ5, became a cultural touchstone. The signal's characteristics were precisely what scientists had predicted for an artificial interstellar transmission. It was a strong, focused beam at the specific frequency of 1420 MHz, a radio quiet band naturally protected by the emission of interstellar hydrogen. Nothing human-made should have been broadcasting from that point in the sky, and no known natural phenomenon could explain such a sharp, powerful, and brief signal from a fixed point among the stars. The search for a repeat began immediately and has never stopped. For decades, astronomers have pointed radio dishes toward those same coordinates, listening with ever more sensitive equipment. The silence has been absolute. The WOW signal was a cosmic one-hit wonder, a scream in the dark that was never heard again. This profound lack of repetition is what fuels both the mystery and the skepticism. Could it have been a natural event we simply do not yet understand? Some have proposed it was emission from a passing comet, specifically the hydrogen clouds surrounding comets 266P Christensen and 335P Gibbs, which were in the vicinity. But detailed analysis shows their known positions did not align with the precise area the Big Ear was observing, and comet emissions are typically broad and messy, not the sharp, clean spike that was recorded. Other suggestions, like a microlensing event or an unknown form of stellar flare, fail to fully account for the signal's unique profile. Its singular nature forces a difficult choice. Either we witnessed an incredibly rare and unknown astrophysical transient, a natural radio burst unlike any other seen before or since, or we briefly intercepted a transmission not meant for us. That possibility, however slim, is what gives the WOW signal its enduring weight. It represents a moment where the vast, impersonal cosmos seemed to speak with a clear, deliberate voice, only to fall silent forever. It challenges our catalogue of natural phenomena and stands as a permanent question mark, a reminder that some cosmic mysteries arrive not as structures, but as fleeting whispers on the radio static of the universe. The silence following the WOW signal feels profound, a reminder of how quiet the cosmos can seem. Yet if we listen with the right instruments, the center of our own galaxy tells a very different story, one written in a language of pure, violent energy. Data from the Fermi Gamma Ray Space Telescope has revealed a brilliant, diffuse glow of gamma rays emanating from the heart of the Milky Way, a phenomenon known as the galactic center excess. This is not the structured hourglass of the Fermi bubbles, but a more pervasive, smooth fog of high-energy light saturating the galactic core. Some of this radiation is expected, produced by known cosmic engines like supernova remnants and rapidly spinning neutron stars called pulsars. But when astronomers carefully subtracted all the light from these catalogued sources, a significant and puzzling surplus remained. A persistent, unexplained glow with a very specific energy signature. This excess is not random noise. It possesses a startlingly smooth and symmetrical shape, concentrated around the galactic center and fading away smoothly with distance. And this precise shape is the first clue that points toward one of physics' greatest mysteries. The distribution of this excess gamma ray light matches almost perfectly the predicted signal for dark matter annihilation. According to leading theories, dark matter particles could be their own antimatter opposites. If two of these particles were to collide in the dense dark matter halo at the galaxy's core, they would annihilate in a flash of energy, producing a cascade of particles that ultimately decay into gamma rays of very specific energies. The smoothness of the signal is key because dark matter is thought to form a vast spherical halo, and its annihilation would produce a smooth, diffuse glow, not a collection of distinct pinpoints of light. The maps from Fermi are compelling, showing this enigmatic excess as a soft, golden haze enveloping the violent heart of our galaxy, a ghostly light that seems to trace the invisible scaffolding of the cosmos itself. Yet in science, a compelling signal is only the beginning of a fierce debate. Could this glow have a more ordinary, if still exotic, explanation? The primary alternative is that we are not seeing dark matter at all, but a teeming population of thousands of unresolved millisecond pulsars. These are ancient neutron stars spun up to incredible speeds by siphoning material from a companion star, and they emit steady beams of gamma rays. If the galactic center is packed with these faint, point-like sources, and our telescopes cannot resolve them individually, their combined light could blend together into a smooth, excess glow that mimics a dark matter signal. Distinguishing between these two possibilities is a monumental challenge that sits at the crossroads of astrophysics and particle physics. One camp searches for subtle irregularities or clumping within the excess glow that would betray the presence of distinct point sources, the fingerprints of a pulsar population. The other refines the dark matter models, predicting exactly what energy spectrum the annihilation photons should have. This mystery is more than an academic puzzle, it is a potential portal. If the excess is indeed dark matter, it would be the first indirect detection of these elusive particles, revealing not just their existence but their behavior and mass. It would mean we are finally seeing the shadow universe not through its gravity, but through its own self-destruction. If it is pulsars, it reveals an entirely new and dense stellar ecosystem at the galactic core, a previously unseen engine of energy. For now, the galactic center excess remains a tantalizing, unresolved signature, a siren song of light from the darkest place we know, calling us to decipher whether we are witnessing the death throes of the universe's hidden majority, or simply the quiet humming of countless stellar corpses. The ghostly light of the galactic center is a puzzle of our modern universe, but to find the origins of cosmic structure, we must journey back to a time when the cosmos itself was in its chaotic infancy. There, astronomers have discovered some of the most ethereal and perplexing formations of all, the Lyman alpha blobs. These are not compact galaxies or sharp filaments, but colossal, amoeba-like clouds of primordial hydrogen gas, some stretching hundreds of thousands of light-years across. They drift in the deep fields of the early universe, glowing with a specific, haunting hue known as Lyman alpha radiation, a wavelength of ultraviolet light emitted when electrons within hydrogen atoms drop to their lowest energy state. In the blackness of the young cosmos, these blobs shine like distant fog-shrouded lanterns, and their sheer size and brilliance present a monumental mystery. What cosmic engine could possibly illuminate such vast, diffuse structures? The leading suspect is a frenzy of creation. Within these blobs, the first generations of stars may be igniting at a ferocious, unprecedented rate. Imagine not just a few stars being born, but entire galaxies worth of stellar nurseries firing up at once, their collective ultraviolet radiation exciting the surrounding hydrogen sea and causing the entire cloud to fluoresce like a neon sign lit by a million hidden bulbs. Another theory points to a more violent power source. As these primordial clouds collapse under their own gravity, they may be funneling vast rivers of gas directly onto the first supermassive black holes at their cores. The incredible friction and heat generated as this gas spirals inward would unleash a torrent of energy, flooding the cloud with the radiation needed to make it shine. A third, more subtle idea suggests the glow is not from heating but from cooling. As the warm hydrogen gas in these overdensities radiates away its thermal energy, it could be emitting Lyman alpha light as it settles and condenses, a cosmic sigh as it prepares to form the first giant galaxies. Deep field images from telescopes like the Subaru and the Very Large Telescope capture these blobs as faint, greenish smudges against the profound black, their irregular shapes hinting at the turbulent processes within. Their existence challenges our most detailed simulations of cosmic dawn. These models struggle to produce clouds of gas so enormous and so luminous so quickly after the Big Bang. The Lyman alpha blobs stand as cosmic beacons from a formative era, their soft glow illuminating our ignorance about how the first structures gathered themselves out of the dark and lit up the universe for the very first time. The soft glow of those ancient blobs marks a time when light first began its journey across the cosmos, but sometimes that journey takes a path far stranger than a straight line. Gravity itself can bend light into a perfect circle, creating one of the universe's most breathtaking optical illusions, an Einstein ring. Named for the physicist whose theory of general relativity predicted it, this phenomenon occurs when two galaxies align almost perfectly with our line of sight. A massive foreground galaxy, or even a cluster of galaxies, acts as a gravitational lens. Its immense mass warps the fabric of space-time around it, creating a cosmic curve. When light from a much more distant galaxy travels through this warped region, its path is bent, just like light passing through a glass lens. In a flawless alignment, this bending distorts and magnifies the background galaxy's light, smearing it into a complete or nearly complete circle of light that surrounds the foreground lens. The Hubble Space Telescope has captured stunning examples of these rings, each one a delicate, fiery halo suspended in the blackness, a cosmic bullseye written in starlight. Beyond their sheer beauty, Einstein rings are not mere curiosities. They are some of the most powerful natural telescopes in existence. The gravitational lens magnifies the light of the background galaxy, often by a factor of 10 or more, allowing us to see incredibly faint, distant objects that would otherwise be completely invisible to our telescopes. It is as if the universe itself provided a magnifying glass, letting us peer deeper into its history than we ever could on our own. but the true challenge these rings present goes far beyond simple magnification. The precise shape of the ring, its thickness, its brightness, and any imperfections in its circle hold a detailed map of the invisible. The lensing effect is caused by the total mass of the foreground object, both its visible stars and, more importantly, its vast halo of dark matter. By meticulously analyzing the geometry of the Einstein ring, astronomers can reverse engineer the distribution of mass in the lensing galaxy. They can determine how much dark matter is there and, crucially, how it is arranged. Is it in a smooth, spherical cloud, or is it clumped in subhalos? This gives us a direct way to chart the architecture of dark matter, something we can do in no other way. Furthermore, these rings provide a supreme test for our theories of gravity on the largest scales. The degree to which the light is bent must match the predictions of general relativity given the observed mass. Any deviation from the expected ring shape could hint at new physics, suggesting that gravity behaves differently over cosmic distances than Einstein's equations dictate. Each perfect circle of distorted starlight is therefore a multifaceted tool, a natural telescope, a dark matter detector, and a gravity laboratory all in one, proving that sometimes the universe's greatest challenges are presented not in chaos but in perfect luminous rings. Gravity's perfect circles reveal the hidden architecture of dark matter, but sometimes that mysterious substance does not just shape galaxies, it becomes the galaxy itself. Drifting through the immense Coma cluster, a city of thousands of galaxies, lies a phantom, a ghostly smudge of light catalogued as Dragonfly 44. At first glance in telescope images, it appears as little more than a faint, diffuse cloud, easily dismissed as a flaw in the lens or a trick of the light. But when astronomers measured its true nature, they were met with a profound paradox. Dragonfly 44 possesses a staggering amount of mass, roughly equivalent to our own Milky Way galaxy. Yet it emits only 1% of the starlight. This means that for every one star you see, there are 99 stars worth of mass that is completely invisible. A galaxy where dark matter does not just dominate, it reigns supreme. This ghostly giant belongs to a class of objects known as ultra-diffuse galaxies. But Dragonfly 44 is an extreme outlier, a cosmic paradox that challenges the very recipe for building a galaxy. Our standard models suggest a tight partnership between dark matter and ordinary matter. A massive halo of dark matter forms first, its gravity acting as a cosmic trap, drawing in vast clouds of hydrogen gas. That gas then cools, condenses, and eventually ignites into stars. The presence of a large dark matter halo should, in theory, lead to a prolific burst of star formation. Dragonfly 44 shatters that expectation. It holds a Milky Way-sized dark matter halo, but its stellar population is pathetically small, a mere sprinkle of ancient stars floating in an immense sea of darkness. How could such a massive gravitational well fail to collect the gas needed to make stars? Astronomers are confronted with several unsettling possibilities. Perhaps Dragonfly 44 is a failed galaxy, a cosmic stillbirth. In this scenario, something prevented the primordial gas within its halo from cooling efficiently. Maybe the gas was too hot from the beginning, or perhaps fierce radiation from nearby galaxies in the crowded Coma cluster sterilized it, stripping away the galaxy's potential before it could ever truly blossom. Another possibility is even more violent. Dragonfly 44 may have been a normal, star-rich galaxy long ago, but as it plunged into the dense environment of the Coma cluster, it suffered a catastrophic encounter. The relentless gravitational tides from other giant galaxies could have ripped away its stars and gas in a process called tidal stripping, leaving behind only the dark matter skeleton and a faint echo of its former self. Yet the galaxy appears strangely intact and symmetrical, not torn and distorted as such a violent history might suggest. This leads to a third, more radical idea that Dragonfly 44 represents an entirely new class of cosmic object, one where dark matter can clump into galaxy-scale structures through mechanisms we do not yet understand, without ever triggering the luminous side of galaxy formation. Deep imaging captures this eerie contradiction, a faint, wispy glow of ancient stars against the black backdrop, a glow that betrays almost nothing of the titanic, invisible mass that holds it together. The existence of Dragonfly 44 forces a fundamental question: is dark matter capable of forming structures all on its own? And if so, how many of these dark galaxies are hiding in plain sight, invisible to all but our most careful searchers? If Dragonfly 44 is a galaxy made almost entirely of dark matter, then its cosmic opposite must be equally shocking. In the constellation of Cetus, a ghost ship sails the void, a galaxy so transparent you can see right through it. This is NGC 1052 DF2, an ultra-diffuse galaxy like Dragonfly 44, but with a revelation that turned dark matter theory on its head. While its cousin is dominated by the invisible, DF2 appears to have almost none at all. The discovery came not from looking at the galaxy's faint, wispy body, but by studying its tiny, orbiting beacons, its globular clusters. These dense balls of ancient stars circle the galaxy like distant moons. By measuring their speeds with the Hubble Space Telescope and the Keck Observatory, astronomers performed a simple cosmic calculation. The faster these clusters move, the stronger the gravitational pull holding them in orbit, and thus the more total mass the galaxy must contain. The results were staggering. The globular clusters were moving far too slowly. Their leisurely pace indicated that the total mass of the galaxy was almost exactly equal to the mass of its visible stars. There was no room left for a massive dark matter halo. It was as if you weighed a sealed, empty box and found it was just as heavy as the cardboard itself, with no hidden weight inside. This was revolutionary and instantly controversial. For decades, dark matter was considered the essential scaffold for all galaxies, the invisible framework without which a large, stable galaxy could not form. DF2 directly challenged that assumption, presenting a universe where a galaxy could apparently assemble itself from ordinary matter alone. The implications were profound. If confirmed, it meant our understanding of galaxy formation was incomplete, and that dark matter might be separable from the visible structures it supposedly anchors. The scientific community reacted with intense scrutiny. Could the measurements be wrong? Perhaps the globular clusters are not orbiting within the galaxy, but are merely passing by in the foreground or background, giving a false impression of slow motion. Or maybe DF2 recently underwent a violent event that stripped away its dark matter while leaving its stars oddly intact. Some researchers even suggested that the rules of gravity itself might be different in such low-density environments, an idea known as modified Newtonian dynamics, or MUND, which could explain the motions without invoking dark matter at all. This galaxy became a critical test case, a cosmic laboratory where competing theories of gravity and structure could be put to the test. Follow-up studies have both supported and questioned the initial findings, with some teams reporting a small but detectable dark matter halo, keeping the debate fiercely alive. Images of DF2 are haunting, a smudge of ghostly light with pinpoint globular clusters scattered around it like distant fireflies. Their slow dance, traced by precise velocity measurements, tells a story that contradicts almost everything we thought we knew. Is DF2 the exception that proves the rule of dark matter, or is it the first evidence of a whole new population of galaxies that somehow built themselves in the light? The ghostly transparency of DF2 challenges the necessity of dark matter, but in the searing brilliance of the early universe, we find structures whose very existence seems to challenge the limits of time itself. These are the large quasar groups, the single largest collections of matter we have ever identified from the cosmos's youth. Quasars are the furious hearts of young galaxies, supermassive black holes feeding at a ravenous pace and glowing with the intensity of 1 trillion stars. They are the lighthouses of the adolescent universe, and when astronomers began to map their locations in 3 dimensions, a startling pattern emerged. They were not scattered randomly. Instead, they clustered into immense groups stretching across staggering volumes of space. The champion among them is known as the Huge Large Quasar Group, or Huge LQG. It is a congregation of 73 quasars, bound not by gravity in a traditional sense, but by their shared location in a filament of the cosmic web, so vast it spans approximately 4 billion light-years from end to end. To grasp that scale, if you could stand at one edge, the light from a quasar at the opposite edge would have begun its journey to you before our own planet Earth had even formed. Its discovery sent shockwaves through cosmology because of one fundamental rule, the cosmological principle. This principle suggests that on the largest scales, the universe should look roughly the same everywhere, a concept called homogeneity. There is an expected upper limit to how big any single structure should be, a scale of homogeneity beyond which no wrinkles or clusters should remain. The huge LQG is larger than that theoretical limit. It is a wrinkle so colossal it should have been smoothed out by the expansion of the universe long before quasars ever ignited. Its sheer size forces a difficult question. Are we looking at a true, physically connected structure, a titanic thread in the cosmic web woven from the densest material in the early universe? Or is this a cruel trick of perspective, a chance alignment where dozens of unrelated quasars, separated by vast distances, just happen to line up from our particular viewpoint in space? This debate cuts to the very heart of how the universe organized itself. If these quasars are truly connected, it means the seeds of the cosmic web, the gravitational wells sculpted by dark matter, grew to an immense scale with breathtaking speed, gathering matter into continent-sized formations while the universe was still relatively young. 3-dimensional maps of quasar distribution make this vivid, showing not just dots on a flat sky, but a depth chart of the cosmos. In these maps, the huge LQG emerges not as a random cloud of points, but as a distinct, elongated chain arcing through billions of light-years of void. Its geometry suggests a filament, a backbone of the early large-scale structure. Yet skeptics point to the statistics of the young, fiery universe, arguing that with so many brilliant quasars shining across such vast distances, some apparent groupings are inevitable, mere illusions in the data. The truth likely lies in a delicate balance, where some groups are real filaments and others are mirages, challenging us to distinguish the cosmic architecture from the shadow play. Either way, the existence of these groups tells us that the early universe was not a placid, uniform soup, but a dynamic, clumpy cauldron where structure emerged on scales that still, to this day, strain the boundaries of our understanding. The immense scale of early quasar groups speaks to a universe born in tumult, and that turbulence is not confined to the distant past. Even now, the heart of our galaxy is breathing fire on a scale we are only beginning to map. In 2019, the Milky Way radio telescope in South Africa unveiled a structure that dwarfs even the Fermi bubbles, a pair of colossal radio wave-emitting lobes that astronomers have dubbed the galactic geysers. These are not the gamma-ray bubbles we discussed earlier, but a distinct, even larger pair of structures, each one a titanic fountain of energy stretching over 4,500 light-years above and below the galactic plane. If the Fermi bubbles are an hourglass, the geysers are the vast, billowing plumes of steam rising from it, a testament to a far more energetic and sustained eruption. They were discovered by mapping faint radio emissions from the galactic center, a frequency that reveals the presence of high-energy electrons spiraling in magnetic fields. The resulting imagery is breathtaking, showing 2 symmetrical, hourglass-shaped outflows that look like a pair of cosmic bellows, exhaling a superheated wind into the halo of our galaxy. What phenomenal engine could drive such an outflow? The source is almost certainly the same as for the Fermi bubbles, the supermassive black hole Sagittarius A star, but the geysers tell a story of a different kind of activity. While the Fermi bubbles might be the remnant of a sudden, violent outburst, the galactic geysers appear to be the product of a more continuous, wind-like process. Think of it as the difference between a volcanic explosion and a steady, powerful geothermal vent. The leading theory suggests that over millions of years, material has fallen toward the galactic center, feeding the black hole not in a single gulp, but in a more regulated, if still furious, stream. As this material swirls in an accretion disk, some of it is redirected and blasted outward along the black hole's rotational axis in the form of a relativistic wind. This persistent wind, rather than a one-time jet, has been inflating these colossal radio bubbles for eons, slowly but surely pushing the surrounding gas of the Milky Way's halo outward. This discovery fundamentally challenges our models of the galactic core's activity cycle. We once thought of such energetic outbursts as rare, punctuated events separated by long periods of quiescence. The existence of two sets of enormous bubbles, the Fermi bubbles and the even larger galactic geysers, suggests a far more complex and layered history. It implies that the center of our galaxy has been episodically active for a very long time, with different modes of energy release creating overlapping structures. The geysers are likely older and more sustained, while the Fermi bubbles might represent a more recent, sharper event. This layered evidence paints a picture of a galactic heart that does not simply beat, but has arrhythmias, coughing and sighing with immense power over cosmic timescales. The impact of these geysers extends far beyond their immediate beauty. They are a primary mechanism for galactic feedback, a process where energy from the core regulates the entire galaxy's evolution. The outflows carry mass and energy from the crowded center and deposit it high into the circumgalactic medium, the thin, hot gas that surrounds the Milky Way. This process heats that gas, preventing it from cooling and falling back into the disk to form new stars. In essence, the geysers are a galactic thermostat, and their immense scale shows just how powerful that thermostat can be. The Mercati radio images make this influence visible, their detailed filaments and smooth lobes tracing the pathways of energy as it sculpts our galaxy's environment. These are not static sculptures, they are active, dynamic features, reminding us that our home in the cosmos is not a quiet island, but a living engine whose breath shapes its own destiny. These galactic geysers reveal the dynamic breath of our own galaxy, but when we train our radio eyes on the wider cosmos, we find structures that seem to defy any known form of breathing at all. Scattered across the deep radio sky are ghostly halos of emission so strange they have earned a perfectly descriptive name, odd radio circles or ORCs. Discovered only in the past few years by wide-field radio surveys like the Australian Square Kilometre Array Pathfinder, these are not fuzzy blobs or ragged clouds. They are stunningly perfect giant rings, visible only in the radio portion of the spectrum. Point an optical, infrared, or X-ray telescope at their coordinates, and you see nothing but empty space. They are radio phantoms, immense circles drawn on the dark canvas of the universe with invisible ink. Their scale is bewildering. A single ORC can be larger than an entire galaxy, spanning hundreds of thousands of light years, and they float far outside the boundaries of any visible galactic core. They are not attached to anything we can see, which makes their origin one of the most compelling new mysteries in astronomy. What cosmic event could possibly create such a perfect, isolated ring of radio waves? The theories proposed are as wild as the objects themselves. One leading idea suggests they are the titanic shockwaves from a cataclysm that occurred billions of years ago. Perhaps two supermassive black holes at the centers of merging galaxies finally spiraled together and collided. The resulting gravitational wave blast could have sent a spherical shockwave rippling through the thin intergalactic gas at the speed of light. As this shockwave expands and interacts with the magnetic fields permeating space, it could light up as a brilliant, expanding ring in radio frequencies, a frozen snapshot of a single universe-shaking event. Another, even more exotic possibility ties them to the theoretical throats of wormholes. According to some complex physics, the mouth of a traversable wormhole, if one exists, could theoretically be surrounded by a ring of hot plasma that would emit synchrotron radiation, which we would see as a radio circle. This is, of course, highly speculative, but it speaks to the level of mystery these circles present. Perhaps the most mind-bending proposal is that an ORC could be the imprint or the bruise left by two bubble universes colliding in a vast multiverse. In this scenario, our cosmos might have brushed against another reality in its infancy, and the energy released at that boundary could have left a permanent circular scar on our sky. The radio images of these structures are hauntingly beautiful, crisp circles or sometimes even bullseyes of emission hanging in a sea of statistical noise. Their very existence is a humbling reminder. Even in an age of magnificent telescopes, a simple, unexplained circle can appear in our data, highlighting how much of the radio universe, the universe of energetic particles and magnetic fields, remains a completely uncharted and mysterious frontier. These ghostly radio circles are a mystery of what we cannot see, but our next cosmic puzzle is defined by what we do not receive. The highest energy particles in the universe are arriving at Earth with a strange and telling silence. They are called ultra-high energy cosmic rays, atomic nuclei accelerated to velocities so fantastic they carry the kinetic energy of a well-thrown baseball, all packed into a single subatomic speck. These particles should be messengers from the farthest reaches of the cosmos, but according to a prediction made over 50 years ago, their very journey should be impossible. This is the GZK limit, named for physicists Greisen, Zatsepin, and Kuzmin. They calculated that any proton or atomic nucleus traveling across the vast intergalactic distances with such insane energy would inevitably collide with the faint, omnipresent glow of the cosmic microwave background, the ancient afterglow of the Big Bang that fills all of space. These collisions are catastrophic for the cosmic ray, sapping its energy in a process akin to a marathon runner trying to sprint through a constant, dense fog. Over a long enough distance, the fog wins, the runner slows down. This means there should be a hard ceiling, a suppression in the number of cosmic rays we detect at the very highest energies. Anything above that limit must have originated relatively nearby, within our own local supercluster of galaxies, because anything from farther away would have been slowed down by the cosmic fog before it could ever reach us. This predicted drop-off in the cosmic ray count is known as the GZK suppression, and it forms an invisible horizon in the sky, a limit to how far these extreme particles can travel. The mystery is that our telescopes do not agree on what they see. Some of the world's most sophisticated cosmic ray observatories, like the Pierre Auger Observatory in Argentina, see a clear suppression right around the predicted energy. Their data shows a steep fall off in the number of particles, a graph that drops away as if hitting a wall. This suggests the physics is correct, and the cosmic microwave background is indeed acting as the universal fog, limiting our view. But other major experiments, most notably the telescope array in Utah, have reported an excess of particles beyond that theoretical limit. Their data shows a curious bump, a cluster of events with energies that, according to the standard model, should not have made it here from distant space. This discrepancy is not a small statistical wiggle. It is a fundamental disagreement about what is arriving at our doorstep. If the suppression is real, it paints a picture of a universe where the most violent accelerators, things like active galactic nuclei or colliding galaxy clusters, are all at a respectful distance, their most powerful products fading before they reach us. But if the excess is real, it implies something astonishing. It means there must be sources of these unimaginable particles within our own cosmic neighborhood, sources we have not yet identified. What could possibly be nearby that is capable of launching atomic nuclei to such insane speeds? Or, even more radically, does this excess point to a breakdown in our understanding of physics itself at these extreme energies? Perhaps the particles are not protons but something else, or perhaps they are finding a way to cheat, interacting with the cosmic fog in ways our current theories do not allow. Diagrams of cosmic ray propagation show this stark choice, with arrows representing particles from distant sources fading away before they cross the GZK horizon, while a few bold arrows from an unknown nearby source punch straight through. The energy spectrum graphs from competing observatories tell two different stories on the same plot. This is not just a debate about data, it is a challenge to our map of the local universe's most violent engines and to the very laws that govern matter at its most extreme. The silence or the unexpected noise at the edge of this invisible horizon may be pointing to an accelerator of cosmic rays hidden in plain sight, or to a new chapter in physics waiting to be written. Even the faint afterglow of creation itself is not perfectly uniform. When we look at the most detailed all-sky maps of the cosmic microwave background, the ancient light from when the universe was just 380,000 years old, we find a whisper of something deeply unsettling. The temperature fluctuations, those tiny ripples that seeded all future galaxies, are not the same in every direction. They appear slightly stronger, more pronounced in one hemisphere of the sky than in the other. This is the CMB hemispherical asymmetry, a subtle but persistent lopsidedness in the very foundation of our cosmos. Imagine the universe as a giant, expanding balloon, and the cosmic microwave background is the inner surface of that balloon, painted with a pattern of hot and cold spots. The cosmological principle, our bedrock assumption, tells us that no matter where you stand on that surface, the pattern should look statistically the same. But our most precise measurements from the Planck satellite and others suggest that from our vantage point, one half of that painted surface has a slightly higher contrast than the other. It is as if the brushstrokes of creation were applied with a slightly heavier hand on one side. The signal is incredibly faint, buried deep in the data and subject to intense statistical scrutiny, but it has stubbornly refused to go away. If it is real, the implications are profound. It would mean that on the largest scales we can possibly observe, the universe is not isotropic. It has a preferred direction, a subtle gradient imprinted at the moment of its birth. This would be a direct and fundamental challenge to the cosmological principle, forcing us to reconsider the very idea of a uniform, featureless cosmos. So what could cause such a fundamental lopsidedness? One possibility takes us back before the beginning. The asymmetry could be a fossil, an imprint from the era of cosmic inflation, the period of faster-than-light expansion that is thought to have smoothed and stretched the infant universe. If the inflationary field that drove this expansion was not perfectly uniform, if it had a slight tilt or gradient, that imperfection could have been blown up to a cosmic scale, leaving one half of the sky with slightly more pronounced wrinkles than the other. It would be a scar from the universe's first trillionth of a second. Another explanation brings the mystery closer to home. Perhaps the asymmetry is not a feature of the universe itself, but a clue about our own motion through it. We know our galaxy is moving, pulled by the great attractor and the dark flow. If we are traveling through a cosmos that is not perfectly uniform on scales even larger than we can see, our motion could create a Doppler-like effect in the ancient light, making fluctuations appear stronger in the direction we are heading and weaker behind us. This would mean the asymmetry is a local illusion, a signpost pointing to an even greater non-uniformity in the unseen universe beyond our horizon. CMB maps with the asymmetry highlighted are deceptively simple, often shown with one half tinted a slightly different color. This visual representation makes the concept clear, but it belies the immense statistical battle behind it. Is this a real feature of the cosmos, or just the luck of the draw, a random fluctuation that happens to look organized from our single, unique point of view? The data continues to be analyzed and debated. This faint whisper in the oldest light we can see may be the most challenging anomaly of all, for it questions not just a structure within the universe, but the fundamental symmetry of the universe itself. 25 cosmic structures, each a riddle written in starlight, gravity, and silence. From the haunting emptiness of the Boötes Void to the impossible perfection of Hoag's object, from the titanic walls that defy the end of greatness to the ghostly dark matter galaxy Dragonfly 44, our journey has crossed the full spectrum of cosmic mystery. We have traced the invisible river of the dark flow, listened to the singular scream of the wow signal, and felt the unsettling chill of a cold spot that might be a bruise from another universe. These are not mere curiosities, they are profound challenges. Each one stands at a frontier where our most trusted models, from the cosmological principle to the lambda CDM model of dark matter and cosmic evolution, are stretched to their breaking point. The universe is actively showing us where our understanding ends, and that is not a failure of science, it is science at its most thrilling. These enigmas are the signposts for the next great leap forward. They are the very questions that will guide the colossal power of the James Webb Space Telescope, the Vera-C, Rubin Observatory, and the next generation of radio arrays and cosmic ray detectors. Every unexplained ring, every coordinated flow, every ghostly glow is a destination for future discovery, a promise that the cosmos still holds secrets capable of rewriting our textbooks. So the next time you look up at the night sky, remember that the darkness between the stars is not empty. It is filled with immense walls and voids, with phantom galaxies and echoes of ancient collisions. It hums with signals we cannot yet decipher and glows with the light of invisible matter. Let that wonder stay with you. Which of these 25 cosmic mysteries baffles you the most? Share your thoughts in the comments below, and if you are hungry for more deep dives into the universe's greatest puzzles, be sure to subscribe. The journey to the edge of understanding has only just begun.